Ever try to list like everything? I mean,
Yeah.
every single thing. Every book ever written, every grain of sand on every beach, every thought you've ever had.
It seems impossible, right?
It does, right. Well, when it comes to numbers, it turns out that's a big fat no.
Hmm.
We're diving into Cantor's diagonal argument,
Oh, nice.
a proof that is both elegantly simple and absolutely mind-blowing.
Mm,
It's so powerful, it completely changed the way we think about infinity.
yeah.
Before Georg Cantor came along, infinity was just this kind of vague concept, like one big endless thing. But Cantor showed us there are actually different levels of infinity, some infinitely larger than others.
What's fascinating here is it all starts with a very simple question. Can you list things out in order without missing any?
Okay, so like, think about all the even numbers. You can always figure out the next one in line. 2, 4, 6, 8, and so on. Keeps going forever, sure, but you could keep listing them out, meaning they're countable.
Exactly, and this lining up works for things you wouldn't expect. All the rational numbers, fractions like 12 or 34, they're countable too. There's a clever way to arrange them so you don't miss a single one.
So you can imagine mathematicians thinking, okay, cool, maybe we can list out all the numbers, even those funky decimals that go on forever.
Right.
But that's where Cantor throws a wrench in the works.
Yeah.
He basically drops this mathematical bombshell and says, nope, not going to happen.
Eh.
He used what's known as his diagonal argument. Picture this, a massive list
Yeah.
supposedly containing every single real number between 0 and 1, all written out with their decimal expansions.
Okay.
Cantor comes along and says, hold on a sec. Shows how to create a brand new number that's guaranteed to not be on your fancy list, no matter how complete you think it is. It's kind of like a mathematical magic trick, using the diagonal of numbers.
It very much is like a magic trick, a clever one at that.
So how does it work?
Yeah.
Walk me through this diagonal magic, because now I'm really curious.
Imagine your giant list of real numbers. Each number has a decimal form that can go on forever. Now focus on the digits running down the diagonal of this list. So the first digit of the first number, the second digit of the second number, and so on.
Uh-huh.
Cantor's method constructs a new number by taking each digit along this diagonal and changing it just slightly. Let's say by adding 1 to each of them.
So if the first digit of the first number is a 1, you'd make the first digit of your new number a 2, and you do that all the way down the diagonal.
Exactly. Now here's the kicker. Because of this clever construction, your new number is going to be different from every single number on your original list in at least one decimal place. No matter how complete you thought your list was, you've missed at least this one and probably many more. Bam. Contradiction.
Whoa. Okay, so that means the set of real numbers is, what's the word?
Uncountable.
Uncountable.
You can't list them all out in order without missing some. There are just too many of them.
It's mind-boggling. It
Oh.
means that some infinities are actually bigger than others. But wait, how does this even work? What does it really mean for an infinity to be bigger than another?
That's where things get even more interesting. It all comes down to this idea of matching things up.
Matching things up.
Think back to our countable sets, like those even numbers. You can pair each even number with a natural number, like 1 goes with 2, 2 goes with 4, 3 goes with 6, and so on.
Right.
It's like a perfect dance where everyone has a partner, even though the dance floor goes on forever.
Right, and that's basically what countable means.
Exactly.
You can find a way to line them up with the counting numbers, even if that line stretches to infinity.
But with real numbers, Cantor's diagonal argument showed us there's just no way to do that. No matter how cleverly you try to arrange them, you'll always have real numbers left out.
So it's like what, like a giant party where there aren't enough chairs for everyone, even though the party is infinitely big?
Exactly.
Okay.
So are you saying that the infinity of real numbers is literally a bigger infinity than the one we get with counting numbers?
Wow.
Precisely.
Okay.
It's like discovering there are different sizes of forever.
Right.
And the forever of real numbers is simply more vast than the forever of natural numbers.
Okay, that is truly mind-blowing.
Yeah.
But now I have to ask, is there a bigger infinity than the one we get with real numbers? Does it just keep going?
That's where it gets even more mind-boggling.
Oh boy.
It turns out there are even larger infinities beyond the real numbers.
Seriously?
Yeah.
How is that even possible?
Well, Cantor's work really opened the floodgates here.
Okay.
It's not just about size, though.
Okay.
It also changes the way we think about describing things mathematically.
I'm intrigued. Tell me more.
Well, if you could list out all the real numbers, You could basically describe each one using its position on that list.
Uh-huh.
It's like giving each number its own unique address in this vast, infinite city of numbers.
So every number gets its own little spot.
Exactly.
Okay.
But because Cantor showed us that's impossible,
Right.
it means there are real numbers that are so complex, so infinitely intricate, that we can't pin them down with any finite description.
It's like they have these infinitely long addresses that we could never fully write out.
Precisely.
Oh, wow.
So even within this realm of the infinite, there are things that we can't fully grasp or define.
Exactly. It's a humbling realization that there are limits to our ability to describe and understand, even in the face of infinity.
It really is.
Wow, that's a lot to wrap my head around.
I know, right?
Before we go any further, can we just kind of recap what we've learned so far? Just want to make sure I'm following all of this.
Of course. So Cantor's diagonal argument shows us three fundamental things about infinity.
Okay.
First, it's not just one concept. It's a
Okay.
hierarchy.
Right.
There are different sizes, different levels of infinity.
Got it. Like layers upon layers of forever.
Exactly.
Okay. What else?
Second, we learned that not everything can be listed out or enumerated.
Okay.
Some sets, like the real numbers, are just too vast for that.
Right, because some infinities are simply bigger than others.
Yeah.
Okay, what's the third thing?
Cantor's argument revealed that there are things in math, specifically certain real numbers, that are so complex they can't even be described with a finite amount of information.
Meaning they're truly infinite in a way that we can't fully comprehend.
Precisely.
That's incredible.
It really is.
Okay,
These are the core takeaways from Cantor's diagonal argument.
gotcha.
It's a seemingly simple proof with profound implications, and it continues to shape mathematical thought even today.
I'm starting to understand why this is considered such a groundbreaking discovery,
Uh-huh.
but it also raises a ton of new questions.
And that's the beauty of mathematics.
Right.
Each answer often unlocks even more fascinating questions.
Well, I'm definitely ready to explore some of those questions.
Me too.
But for now, let's move on to the wider implications of Cantor's work and what it means for our understanding of infinity. So we've established there are different sizes of infinity,
Yeah.
but does that mean there's some ultimate infinity out there, some kind of mega infinity that's bigger than all the rest? Or do these levels of infinity just keep going forever?
That's a question that has kept mathematicians and philosophers up at night for a long time. Cantor himself actually believed there was an absolute infinity, which he called the absolute infinite. But he thought it was so vast, so beyond our comprehension that we could never truly understand it.
So it's like the ultimate mystery of infinity.
You could say that.
Yeah.
But here's the thing, even without grasping this absolute infinite, Cantor gave us the tools to explore the infinite in ways we never thought possible.
Okay.
It's like he handed us a map to this incredible uncharted territory, even if we may never reach the final destination.
I like that analogy. So what are some of the routes on this map? Where did Cantor's work lead us?
Well, for one, his diagonal argument led to the development of what are called cardinal numbers.
Cardinal numbers.
Yeah, these are essentially labels that let us classify and compare different sizes of infinity.
So instead of just talking about countable and uncountable, we can actually give names to these different infinities.
Exactly. So we know that the infinity of the natural numbers is called Aleph null, while the infinity of the real numbers is Aleph 1.
Okay.
And there are even bigger ones beyond that, a whole hierarchy of infinities, each with its own cardinal number.
Hold on. So you're saying there's an LF2, an LF3, and so on?
It gets even more complex than that. But yes, the idea is that there are infinitely many levels of infinity, each bigger than the last.
My brain is officially exploding.
I know, right?
But it's a good kind of explosion.
It is a good kind.
It is, it is.
And it's not just an abstract mathematical curiosity either.
Right.
This system of cardinal numbers has huge implications in fields like set theory, logic, computer science, and even theoretical physics.
It's amazing to think that one argument about listing numbers could have such a widespread impact.
It really speaks to the power of mathematical thinking.
Yeah.
Sometimes the simplest ideas can lead to the most profound discoveries.
Okay, well, I think we've officially reached peak mind blown for today.
Yeah, I think so too.
Well, before we wrap up, what's the one thing you want our listener to walk away with from this deep dive into Cantor's diagonal argument?
I'd say it's this. Infinity is way more complex and fascinating than we usually give it credit for. Cantor's work challenged our assumptions and revealed a whole universe of mathematical wonder.
It really makes you realize that even in the vastness of infinity, there's structure, there's hierarchy, and there are probably countless mysteries still waiting to be uncovered.
Absolutely.
Who knows what other levels of infinity are out there?
And who knows what those discoveries might tell us about the nature of the universe and our place in it. Cantor's work is a testament to the power of human curiosity and the boundless possibilities of mathematical exploration.
Beautifully said. And on that note, we'll leave you to ponder the infinite. Until next time, keep diving.